work out how to do is how to share my screen. So you're all being recorded, folk. So watch what you say. And where is sharing? There's another big button there. Share screen. Right. Okay, so there's some slides that go with this talk, and I've put the slides already onto Teams, make them available afterwards as well. The topic this week is iterators, generators, references, and assignments, and this follows on from what we covered last time, which was closures and decorators. And generators are surprisingly similar to closures in some way. Hi, Vincent. Glad you could make it. If you do have any questions, hi. I don't mind being interrupted. I like being interrupted. I like questions, and I like to make sure that you can all that you're all following. So if there's anything that's not clear, it's probably not clear to other people as well. So please do ask. So we're going to look at iteration in general and generators in particular. Now, here in Gigaclear, we use coroutines. We do a lot of async programming, and so a full coroutine, we can define a function. And this was just me playing with it earlier. Let me bring it down. I import async IO. I use the async def. This defines a coroutine function. It doesn't await in it. And you'll notice if I call the main function, it doesn't start executing code. It produces a coroutine object. And then one of the things we can do is we can get the event loop from async IO. Async programming still runs single-threaded. I'm going to do another session on concurrency, and we're going to look at threads and multiprocessing for true concurrency, running more than one thing at the same time. Async programming is a way of getting the appearance of concurrency. You can do multiple things at one time, but we're running single-threaded. You have an event loop that manages the tasks, and every time something awaits, it yields control to the event loop, and the event loop looks at all of its waiting tasks. It will run something else until this is ready to return. And there's a convenient break, and the event loop gets control. So here I've fetched the event loop from async IO. If you've ever done any GUI programming, or you've done any JavaScript programming, you've done async programming as well. So here I'm going to run the loop until complete with a coroutine. You can see this code, it just sleeps, and then it prints done. So those are coroutines. We're already using coroutines. But the way we use them, that's only half of coroutines. And so before we look at the other half, let's look a little bit at generators, the iteration protocol. The iteration is very common. It's fundamental to computer science. It's been demonstrated that anything you can do with recursion, you can also do with iteration, with looping. So it really is fundamental to Python. And it also turns up in a bunch of places anytime you do tuple unpacking or you compare sequences. There's iteration going on under the hood. So you have a simple, we have some numbers. Maybe I shouldn't do this right at the bottom of the screen. No, it's going to be more complicated to try and change that. Okay, I'll carry on. Numbers equals 1, 2, 3, 4. We have a simple loop for x in, or let's call it for num in nums. Print num. So in terms of syntax, we have the for statement. This is the iterable. A list is a sequence. Every sequence is iterable. We can iterate over every sequence. And this is the loop variable, num. So every time through the loop, the variable num gets assigned to a new value. And this is the body of the loop indented inside the for statement. That's nice and straightforward. We execute this, and exactly what you think will happen happens. 1, 2, 3, 4. What you may or may not know is this all happens in the same scope. So it's telling me that coroutine object got garbage collected without ever being awaited. Never mind. So after the iteration, the loop variable num is still bound. But iteration, like most things in happens via a protocol. And protocols in Python mean the magic methods, the double underscore methods, the dunder methods. And this protocol here shown on this slide, this is exactly equivalent. This code here is exactly equivalent to the code above, for x in obj. Now we can't, although nums is iterable, it's not an iterator. If I call next on nums, it's not an iterator. And the reason there's this extra object involved, this iterator object involved in iteration, and it's there to keep state. I'll show you why we need it. We can do for x in nums, we can do for y in nums. I'm doing 2 simultaneous iterations over the sequence nums. Prints what you would expect. And so the state is not kept, the state of the iteration is not kept on nums or anything like that. There's an intermediate object, an iterator, which keeps track of the iteration itself. And we can get one of those. There's a built-in function called iter. So this will get me a list iterator object, a built-in object. And it's exactly the same thing. This is quite common in Python, that we have a protocol and a protocol method, the dunder iter method, and there's a corresponding built-in function to access it.
Michael, is it?
Yes.
Is this a list iterator because nums is a list? So
that's right. Yes. Yeah.
Tuple iterator otherwise, or
yeah, that's a good point. I would expect it's a slightly different type. Yeah, tuple iterator. So I is our list iterator. And you can see the protocol involves, we obtain an iterator from the object. We repeatedly call next on it, on the iterator object, to obtain an item. And at some point, this iterator raises a stop iteration exception, which tells Python the iteration is complete. So they do say you shouldn't use exceptions for control flow. Well, Python kind of bakes exceptions for control flow into the iteration protocol. So the cat is already out of the bag. So this iterator has a dunder next method, which I can call. This will fetch me 1. There's also a built-in next function, which it will advance an iterator 1 step through. So simulate a single step through an iteration. So I can call this repeatedly. And now calling next will raise stop iteration because the iterator is exhausted. Same iterator, same. So this is the iteration protocol, and everything that we iterate over implements this protocol. First, we call dunder iter, which obtains an iterator object. The iterator object keeps the state of the iteration, and dunder next is called on that repeatedly until you get to the end of whatever it is you're looping over, and then the iterator raises stop iteration. So all iteration in Python implements this low-level protocol. You can imagine that if you wanted to make your own objects iterable, that's a bit of a pain. This is what we've just done. But if you have custom objects that you're implementing, say we have a portfolio object, for example, and it stores the actual data in a private variable, self._holdings, which is a real list, we can make portfolio itself iterable simply by delegating to the iter of self._holdings. So we don't need to implement the full protocol. The real data is stored in self._holdings. We can delegate there to the real iterator. So that's one example of using object composition. And it saves us having to implement a custom iterator. There is, however, a better way. Generators. Generators provide stateful iteration, and generators are coroutines. They're coroutines that use the yield statement. So when I call that main function above, which is an async function, it produces a coroutine object. Generators are very similar. Generators are also coroutines, but we're going to use the thing about coroutines is let's do CO equals underscores. The full definition of coroutines from a computer science point of view is that you can suspend and resume execution. You can pass values into them, receive values out of them, and exceptions can be raised inside of them. So for sending values in, when you await, when you're inside a coroutine, you might do something like x equals await and some function. Sleep is not going to return anything. What happens is when that result is ready, the event loop is going to send the value in using the coroutine send method. It's only just been started, so that doesn't work. This is not a coroutine. The event loop is not running. And you can also throw attribute errors. You can also throw errors inside the coroutine. Those are the aspects of coroutines that we're not going to use in generators. So I'm going to write a simple generator function. Generators are great. They provide stateful iteration. They provide a way of implementing the iteration protocol without having to manually implement those _iters and _next methods. So here's a simple countdown generator. So there's no return in this function. I'm using yield. And this is a generator function. Any function which uses yield is a generator function. Coroutine, a type of coroutine. So you will notice when I call, the very first thing this function does is print. And yet when I call it, there's no output, just like with the coroutines we use for async IO. Calling a generator function does not start code execution. It produces a generator object. This is a one-shot. It's not reusable. If I wanted another one, I have to call countdown again. But a generator object is iterable. It's designed to be used in iteration. So I can start execution by calling next on it. So as soon as I call next, execution starts here. Num has the value of 5. We go into a while loop. Yield num. And so this is how the coroutine functionality is used. Execution stops here. The generator yields the number 5. And it's not just the value that's yielded. Control flow now comes to me. I can do whatever code I want. Print hello. So the important thing about a generator is it doesn't just yield a value, it yields control flow. And when I call next again, execution is going to resume where it left off. Execution was paused. So now num minus equals 1, num will have the value 4. We'll go back into the loop. The while loop, yes, num's still true in a Boolean sense, so we'll yield 4, and 4 will be yielded, and then 3 will be yielded, and you can see where this is going, 2, 1, and now the generator is exhausted. If we want to do this again, we create a new generator object. But stateful iteration, because if we'd implemented an iterator object that had a dunder_next method, in between every call to dunder_next, we'd have to store the state, retrieve it, update it, and then store it again. And this is all kept in local variables. The state of the iteration is all in local variables, in the local variable n, in this case, or nums, I think num I called it in mine. So the generator objects that we get, they have the dunder_next and the dunder_iter. The generator implements the iteration protocol for us. It was surprisingly easy to add generators to the Python language. Generators came before the full coroutine functionality. And normally when you call a function, it creates a stack frame object. That stack frame has an array for all of the local variables. It has a pointer to the, or a reference to the bytecode of the function object, and a counter whereabouts in the bytecode execution has got to. And the interpreter keeps a reference to the current stack frame that code is being executed in. And normally when you return out of a function, the interpreter decrements the ref count drops to 0, and the stack frame object is returned to a zombie pool to be reused. The big difference when we encounter a yield is the stack frame is still in use. So we don't drop that reference count. It's still around. We've still got the counter as to where we are in the bytecode. So when execution resumes, we just carry on where we left off. It was a very simple, it was adding the new syntax was harder than adding the functionality internally.
Sorry, Michael, I wanted to ask you, we have our generator, what you've written, but we don't have any condition for stop the while in your code, but we are stopped at 0. Why?
Yeah, because we drop off the end of the function, a return immediately exits.
Why do we have stop iterations?
That's the iteration protocol. When the function stops executing, the generator is exhausted, and the generator object itself, which is kind of like a wrapper over this. If you look, the generator here has dunder_next and dunder_iter. We didn't write those either. If the function has come to an end, the generator knows to raise stop iteration.
I was expected what we will get the -1, -2, -3.
No, because look, when num gets to 0,
sorry. Okay.
This loop will
yeah.
that while statement will no longer be true. It will be false.
It only now.
Yeah. While num, where as soon as num hits 0, that's false. Execution stops. Generators are surprisingly useful. There's all sorts of things you can do as, and you can use them to make context managers as well. So generators are full of coroutines. You also have this .send method to send data into them, .throw to raise exceptions inside them, and you can do exception handling inside them. But that's not the topic of today's knowledge share. But it's important to note they behave. You're probably used to this from the way that we use coroutines already in async programming. The countdown there, when I call countdown, it doesn't start code execution. It creates it needs an argument, doesn't it? It creates a generator object. Code execution starts when iteration starts. Everyone happy with that? So the yield keyword, any function with the yield keyword in it, is a generator function. The yield keyword, it yields a value and it yields control flow. When we call next, or the next step in the iteration, execution carries on where it left off. Execution is paused and resumed, fundamental properties of coroutines. I've covered all of this. So if you want to make objects with custom iteration, rather than having to implement done to iter and done to next yourself, you can quite simply make the done to iter object of the done to iter method of your object. Now instances of thing are iterable for val in T. Val. And every time you iterate over the object, done to iter will be called, and it will return a generator. So you can make custom objects iterable by implementing done to iter as a generator function. And if you're implementing your own containers, that can be your collection objects, that can be handy. Okay, any questions on that? On generators. I think we might get away with less than an hour. Let's see how we get on. Okay, so the next topic is one that is it's fundamental to Python, and it's fundamental to how Python works. So I think it's really if you want to have the right mental model about how things like variables and function calls work in Python, it's some details that are important to cover. So it's a little bit low level, a little bit basic. You probably know almost all of this anyway, but it's worth covering and worth understanding. So in Python, everything is an object. Every object has a type. You can only perform operations appropriate to the type, and it's the type that's responsible for creating new instances. That's the object-oriented jargon of Python. Everything is an object, but just as everything is an object, everything is a reference. The only way you can ever do anything with objects is through references. And the most fundamental way we do that is through names and the assignment statement. Oh, come on, give over. Okay, so x equals 3 plus 2. That's a straightforward assignment statement. It has two sides, the right-hand side and the left-hand side. First, the right-hand side is evaluated. That evaluates to an object, the integer object 5 in this case, and then the name on the left is bound to, refers to, points to the object on the right. So the name x is a reference to the integer object 5. And we actually use, Python actually uses reference counting for garbage collection. So when the reference count on an object drops to 0, there is it is immediately collected. I think it's sys actually, that's what I'm looking for. Input sys dot get ref count. So every object under the hood, every object is a C struct. Pi object is the basic C struct and the built-in types like list and dictionary, they extend PyObject. So every object has a field for the reference count, it has a field for the type, and these all exist on C structs. So the reference count is just a field on the C struct. So let's have a look at X. Wow, the integers 0 to 255 are immortal, and there's only ever one of them. So X is the integer object 5, and at the moment there's about, in Python, there's 1 million references to the integer object 5. Let's try that with 256. (256) ought not to be interned. Ah, there we go, 2. But there are lots of ways we take references to objects. You can put them in a list. You can attach them as attributes to another object. You can put them in a dictionary. You can pass them to a function. And all of these different ways of taking reference to objects, none of them copy the object. A reference copy. Under the hood, a reference is a pointer. We try not to talk about pointers in Python because Python names in particular have different semantics to traditional pointers. But under the hood, a reference is essentially a pointer. Okay, so this is it's not a trick question. It's just perhaps a slightly tricky question. Here we've got 3 lines of code. A equals 1, 2, 3. B equals A. C equals A, comma B. In these 3 lines of code, how many different list objects are there? Someone have an answer?
It feels like QI and we're about to get the burp, burp, burp.
It's not a trick question. It's just potentially slightly tricky. How many different, those 3 lines of code?
2?
Yes, well done. Yeah. So let's look at these and let's look at what happens in each line. So you can tell the first line A here, A equals 1, 2, 3. There's that square bracket syntax. 1, 2, 3. That's the list literal syntax. It creates a list object. So at that point, we have this list object with 1A. The name A is bound to, the name A refers to that list object. B equals A. This is an assignment. The right-hand side is evaluated. The name A evaluates to the same list object. So the name B is now bound to, refers to the same list object. So you've now got one list object, this line here with 2 references to it, the names A and B. Then this third line, again, we've got the list literal syntax. So there's a real list being created there. So that's the second list. And in index position 0 of this list is a reference to the list pointed at by A. So you can see here. And then in index position 1, the second index position, there's another reference to the same list. We got there via the name B, but it's the same list. So we have list C is a new list with 2 references to the existing list. So we've got one list here, which has a reference A and a reference B, and 2 more references from the list C. So the reference count on it should be 4. Does anyone know what, this is a trick question, what sys.getRefCount will return when I call it on that list? Anyone guess? Anyone know the answer?
On C? Or
on the
A?
list A.
3.
It's going to return 5. because all it does is read the reference count field on the object. And when you pass an object in to sys.getRefCount, getRefCount gets a reference, takes another reference to an object. So it always inflates the reference count by 1. I wish right at the very beginning they just had it deduct 1 from the answer. But yeah, sys.getRefCount will tell you how many references are to the object, including the reference it holds itself. There's also, if you want to play around with this kind of stuff, there's some handy stuff in the GC, the garbage collection module, as well as Python uses reference counts for garbage collection. So when the reference count object on an object drops to 0, it is deterministically immediately collected. You can have object cycles, though, where every object in the cycle has a reference to another object, so the reference count on none of these objects will ever drop to 0, but none of the objects are in use, so that Python has a cyclic stop the world garbage collector, run every few hundred bytecode ticks in the interpreter loop. And there's a couple of interesting functions, more useful for debugging than for actual use. You can tune how often that garbage collector runs, and you can get the referrers for objects, get the reference. Sometimes useful when you're trying to track down memory leaks. So the GC module is can be handy at times. All right, so you got that one straightforward enough. But let's have a look at this. We have our list A. A is B. A and B are the same list. And we have our list C. So we do A.append. We've got our list A. We merrily add something to it. And lo and behold, C has changed. B has changed. And all we did was append to A. And this is because A and B are references to the same object. So when we modify A, we would expect to see B change. And similarly, inside C are two different references to the same object. So none of that code created any copies, and lists are mutable. They can change. So changes to mutable objects show up anywhere where you have a reference to that object. If you pass a function to pass a dictionary to a function, and that function modifies the dictionary, you'll see the change because dictionaries are mutable. This is by design. It's how mutable objects work, and any language that has mutable objects will have this same issue. So functions also receive a copy of objects. We have a function here called function. It takes a dictionary as an argument. And you can see from the code there, we pass the dictionary in, function modifies the dictionary, we can see the change. So there isn't really, in computer science, used to talk about call by value and call by reference. Call by value, things would always be copied in. With call by reference, you could modify what the reference pointed to. You could point it to a completely different object altogether. And Python is neither call by value nor call by reference. So we call it call by object. The function receives a new reference to the object. So technically it's call by value, where the value is a copy of the reference to the object. But call by object is a useful way to describe it. And hopefully you can see there what's happening. And this is why it's also useful to know that the primitive types, int, float, bools, they're all immutable. Strings are immutable, unlike in Ruby. And you can pass them around anywhere in your code, and they're not going to be modified by other code. Tuples are immutable. You can make frozen instances of data classes, which are immutable. Sometimes immutability is useful. But let's try another question to check you understand references in Python. Again, this is not a trick question. You probably all get this pretty easily. You're all used to Python more than other languages. When I teach people that are coming from sort of C, C++, Java, etc., they sometimes don't get this so easily. So A, create a list. The right-hand side is evaluated. This is the list literal syntax. A list object is created. The name A is bound to point to that list. Then we execute the code B equals A. So B is now pointing to the same list as A. We do A equals 4, 5, 6. What is the value of B now? Vincent,
1, 2, 3.
Yes, well done. And this is in a way why we say that Python doesn't really have variables. It has names that refer to objects or names bound to objects. Because variable syntaxes in syntax in many languages, B would now be pointing to 4, 5, 6. But let's look at what happens here. Well done, Vincent. Thank you. A equals 1, 2, 3. We create the list object. The name A refers to the list object. Then we execute the line of code B equals A. So A is evaluated. The right-hand side of that assignment set is evaluated. A evaluates to the same list object. So the name B is now bound to, refers to that list object. We've got one list object with 2 references. Then we do A equals 4, 5, 6. This creates a new list object. See there, the literal syntax. There's a new list being created. And so the name A, we call it a rebind operation. The name A is no longer bound to the original list. The reference count there is decremented. And the name A is bound to, refers to the new list object. But the name B is unaffected, was left pointing at the original list object. So this assignment here does not affect any other names. And this behavior, it comes out as a consequence of the fact that Python is built on top of dictionaries. So every module has a name. Every even the main code you're executing, so the name of this module, every code is executed in a module, even the main script. So the main script will have the name dunder main. That's the namespace I happen to be in. All modules, when you import them, are cached in sys.modules. That's a real Python dictionary. So any module can fetch itself out of sys.modules, get a reference to the module object by using its name. That's a module object. But the interesting thing is the dunder dict is the setter, is the dictionary of all the global variables in the current namespace. So the globals, let's do globals.keys. A module forms a namespace. The keys are the variables. And the collection of global variables, this is the dunder dict. So when I do X, Y, A, there's a lookup in the module dictionary is happening. And the semantics, the behavior of these variables come about because this is how the names are stored. So this brings us to the difference between identity and equality. Suppose we have 2 lists, A equals 1, 2, 3, B equals 1, 2, 3. They're 2 different lists. They are equal, however. List equality is if 2 lists have the same length and each member is equal, the 2 lists are equal, but they're not the same list object. Every object has, unique for its lifetime, an ID, and in CPython, the standard reference implementation of Python, that's related to its memory address. So we look at the ID of A, it's a number, ends in 0640. If we look at the ID of B, ends in 3040. they're different objects. They have a different ID. So although A is equal to B, A is not B. They are different objects. And obviously, because they're mutable, A can change. And now A is no longer equal to B because they were separate objects. So the difference between identity and equality. So we have the equals and the not equals operator for checking identity. That's the inequality operator. We have the is and the is not operators for checking identity. And none, true, and false are all, well, none is a singleton. True and false, there's two of them. You can't really call them singletons, but there's only two of them. Any true in the language will always be the same true. So if we do x equals false, the correct way, Pepe will pick you up on it. The correct way to compare against Booleans is to use is and is not. And the identity check is faster because under the hood, it's just a pointer comparison. So is and is, if you mean to check for identity, use is and is not. Okay, so we've looked at the problems with mutability.
Michael, sorry to interrupt. You mentioned that true and false are not singletons because there are two of them. Can you expand on that?
So the singleton pattern is where you have a class that has one single instance and it cannot be reinstantiated.
Oh, I see.
So none is a true singleton. If we look at the type of none, we're going to get none type. And if you try and instantiate it, it will just return instantiated is none. So there's me trying to instantiate a new instance of none, and it returns the same one. Whereas the type of true is bool.
That's brilliant.
But there are two instances of the bool class, true and false. So it's not, it's a doubleton rather than a singleton. You can't create new bools. You can't create new instances of the Boolean class that are something else, but it's not a true singleton. Does that make sense?
Yes, I guess so. I was thinking about the objects more than the types. But
right,
yeah.
but the definition of a singleton is a singleton is an instance of a class that can only have one instance, and true and false don't meet that strict definition. They're kind of like Booleans. And you can't code a true Boolean in C Python, in standard Python, sorry, with standard Python code. You can't make something that behaves as a true Boolean. Anything written in Python, you can create a new instance of. Topic for another day, perhaps, right?
Thank you.
Okay, ID is an integer unique for the lifetime of the object. So let's have a look at one of the problems with mutable objects. Anytime you're performing an operation, a destructive algorithm, 1, 2, you need to know, is this my data structure to modify? So here we have a data structure that's come in. I mean, and note even sorting a list is destructive. The order of things in a list is information. If you sort that list in place, you've lost the information about what the order was. So anything that adds to a list, removes from a list, changes the order is a destructive algorithm. And suppose we've got this list A, it's a nested data structure. Maybe it came in from JSON over the wire. We want to perform a destructive algorithm on it. So being good programmers, we're going to take a copy of it. There are at least 3 ways to copy a list. You can copy any sequence by slicing it from beginning to end. That will always create a copy. That's one way. Lists and dictionary now have copy methods. That's another way. My kind of preferred way is you pass the list to the list constructor. It will create a new list with the same content. I think that's nice and obvious what that is. So now A is not B. They are different objects. The ID of A is different from the ID of B. List A and B are different. And if I do A.pop, pop something off the list, see A has changed, B has not changed. We've taken a copy of the object. So then I'm modifying. I ought to be modifying 2. B was the copy. But anyway, A2, we're going to, let's amend this. So A has changed. And look, horror of horrors, B has changed as well, even though we took a copy. And the problem is we were working with a nested data structure, a list containing a list, and we only took a shallow copy. And let me take you through what happened. Most of the time, whenever you're working with code, you tend to know, am I working with flat data or am I working with nested data? Part of the zen of Python, flat is better than nested. Import this. Namespaces are one honking great idea. That's great. Those 2 lines need some explanation, but are fantastic. Errors should never pass silently unless explicitly silenced. Readability counts, the most important one. Flat is better than nested. That's what we're looking at now. But you usually know, is my data, am I working with a flat data structure or am I working with a nested data structure? If you're working with a flat data structure, shallow copies are fine. But let's have a look at what list A is. Don't forget, everything in Python is an object, but everything is also a reference. The contents of the list are references to the contents of the list. So in list object A, integer position 0 is a reference to the integer object 1. Index position 1 is a reference to the integer object 2. Index position 2 is a reference to this inner list, 100, 100, 999. Index position 3 is a reference to the integer object 3. We copied that list, so we get a new list object, and inside that, it's a copy. It's a list with the same contents. It's a different list with the same contents. So at index position 0 of B is a reference to the integer object 1. Index position 1 of B is a reference to the integer objects 2. And in index position 2 of the list B is a reference to the same list object. They're sharing that inner list. And did you see I got to flip you the bird there? Sorry. Right. Because we only took a shallow copy. So if we go back, we have A, we have B, A is, B is false. They are different objects. But A2 is B2, that inner list, they both have a reference to the same inner object. So when we modified that inner list, the change showed up in both places. If you're ever in a situation where you need to do that, you use the copy module and you take a deep copy. And deep copy is pretty complex code. You can't copy objects with, it knows how to copy arbitrary objects. You can copy instances of most things. You can't copy stuff with opaque system state. You can't copy a socket. You can't copy a file handle, that kind of stuff. It has the same restrictions that Pickle has for serialization. Copy.copy exists for making shallow copies, but taking a shallow copy of an object is usually easy anyway. So copy.deepcopy is the function that gets used. So if you have a function that takes a data structure, it's going to perform a destructive operation on that data structure. You need to sort some of the lists, consider whether you need to take a deep copy of the data structure first. Is everyone happy with that? As to what the purpose of deep, it's fairly complex code. We don't end up using it very often, but sometimes you need it.
We use deep copy quite often in the plugin.
Do you? Yeah.
But it's super slow as well, because sometimes you're copying big asset collections. And
yeah, and it knows how to handle recursive objects, and so it's quite complex code. There's this principle, Spolsky's law of leaky abstractions, that if you're you can only safely work at any level of abstraction if you understand the layer below, or have some understanding of the layer below, because abstractions leak when something goes wrong. It happens in the layer below the level you're working at. And so I try to avoid deep copying for the same reason I try to avoid pickle, is because in order to use this code, I don't ever really want to have to understand what they're doing underneath. But it's well worth being aware that they can be slow, yeah. How much time have we got left? Have we got 5 minutes? We've got about 5 minutes. Everything is an object. I think I've banked that into your heads enough. And I like this slide because it shows a nice simple consequence of
Michael?
function. Yes?
Sorry to interrupt you. Before you move on, you mentioned you try to avoid deep copy. I think one of the use cases that I have in mind is when you're trying to iterate with something whilst you're modifying it.
Yes.
There might be ways to do that without it, but it can be quite a sort of explicit, simple way of doing that.
Iteration is typically over a flat data structure. So suppose I had, what have we got here? A. If I want to iterate over everything that's A, but possibly
remove some items depending on something that might exist in the original list.
Iterating over a shallow copy should be.
Yeah, that might be sufficient.
A shallow copy should be sufficient there. I appended A instead of item. yeah.
But yeah, you're right. A shallow copy might.
Because iteration is a flat. But yes, you mustn't amend. You mustn't modify things you're iterating over directly. Mm-hmm. That is a rule of Python. Well,
I think I probably find myself avoiding shallow copies instinctively because of, at least with a deep copy, you sort of you don't have to think about it twice. You tend to know where you stand. Shallow copy might end up having side effects that you might.
I mean, it avoids you having to understand your code.
Yes, that's what I meant. People will notice that I'm no longer Michael's line manager. That's obviously, I'm joking.
So I can afford to be rude.
You could be rude before.
Oh right! Wow. Okay. All right. I better stop being rude then. Right. Let's have a look. What did I just do? A is a very big object now because I just appended stuff to it whilst we were iterating over it, and the iteration never ended because I was extending the list as I was looping over it. You're very much not supposed to do that. And taking and iterating over a copy of the list, as Vincent so eruditely pointed out, can avoid that problem. Everything is an object. The last couple of slides are really just for fun. Another standard library module you may not be aware of, the operator module, has all the standard operators, including the operators for fetching things out of lists and dictionaries, and all the addition, etc., are available as functions. So you might, if you had some, say you had some code that was wanted to perform an operation on some operands based on an operator, you could write it as an if-elif chain, and you can see there how much it sucks, especially if you have to repeat that code. So you can instead build this as a dictionary where the key is the operator and the value of the functions. We can just put the functions straight into the dictionary as objects, as values. And then calling the appropriate function is as simple as fetching it out of the dictionary, because functions are just objects, just like anything else in Python. We don't have to build a function registry. A dictionary will do the job just fine. And we have match case in the language as well now, but I still, this sort of pattern is useful, and you see it in Python a lot. And really, I like to do this example just to show that really everything is an object. Import math. That's the absolute built-in function. That's the math module, and that's an exception type. They're now all in a list. So items 0 minus 33. I can call the abs function from a list if I have the correct syntax. I get to call my favorite standard library function, math.squirt. And you can even do this, which is actually horrible. And I really don't think you should be allowed to do. No, it's accept, isn't it? Accept items 2. So you can dynamically pick which exception we're going to handle. Fetching it out of the list at runtime works because absolutely everything in Python is an object. And I will leave you the very last thing for today. This is a little bit of a Python koan in that it is entirely useless knowledge, but understanding why the behavior is requires such a foundation in Python that the foundation and context is useful rather than the knowledge. Should this print true or false? Code at the bottom of that screen there. The ID of empty list, is it equal to the ID of another empty list?
There's a subtlety, but I think it's going to be true. I remember instantiating list with the list function instead of empty list, but I'm wondering if there was something related to namespace.
I'll take you through what happens. You are correct. It does say true. I mean, let's do it the other way. First, if we do x equals empty list, y equals empty list, the ID of x is obviously not equal to the ID of y. They're different objects. However, if we do this, we get the surprising result, true. And this is because of two things, one of which I've told you, and one of which I haven't. Well, three things. This is an equality operator. So it's a left-hand side. So it's a binary operator. It has a left-hand side and a right-hand side. The left-hand side is evaluated first. Python creates an empty list. That is immediately passed to the ID function. The ID function gets the ID. It returns the ID, and it decrements the reference. When the list leaves the ID function, it decrements the reference count, and there are no other references to that list object. It is immediately garbage collected. It happens immediately. The reference count drops to 0. With the right-hand side is then evaluated. What happens when it's garbage collected is the small garbage collector, the small object allocator says, ooh, an empty list object, they're really handy. I might be asked for one of those. Instead of freeing it up altogether, I'll hold on to it. And then lo and behold, on the right-hand side, the small object allocator is asked for another empty list, and it goes, oh, I've got one of those hanging around. Here, you can just have that one that I was, and it returns the same list object. And I did say the ID of an object is unique for the lifetime of the object. But IDs can be reused. So this empty list is garbage collected on the left-hand side and then brought back to right on the right-hand side. And even fairly experienced Python programmers won't know why that happens. So it's a useful trick to be able to pull out.
I've put in the chat what it reminded me of, which was a case around default parameter instantiation.
Ah, yes, yeah, that's another gotcha that will get that will catches most people at some point. The default value is evaluated at function creation time. There is a proposal going through for a special syntax for late binding. So there will be a way of we might get a way of specifying creating a new empty list. But yeah, that's a common gotcha. You've got one list there. Any other questions or comments before we finish? That's all I had for you.
What's the next one about? Already.
I was going to do Unicode floating point numbers, just because I can't mention Unicode without mentioning floating point numbers and regular expressions, Unicode and regular expressions, if that's
Cool.
Stop avoiding the mock test.
The thing with mock is I don't normally teach. You'll have to write that from scratch. So I am putting that.
I'm begging you.
There will be one. There will be one. I promise. All right. Alexandra, did you have something to say? I saw a hand go up. And... No.
Oh,
Okay.
I wanted to use these clap hands and misclicked.
Oh, I see.
Thank you.
All right, folks. Yeah. Are you up for another one next week? I don't want to take up too much of your time.
Yes.
Yeah.
Because you are, Vincent.
I'll put one in for next week then. Thanks, folk. I really enjoy doing it. Thanks for coming along. And the recording should appear in this channel. That's fairly soon.
Thanks, Michael. That was great.
Thanks ever so much. That was
Thank
great.
you.
Thank you.
Cheers.
Thanks.
Bye.
Bye now.
Bye.